Gunpowder can level a castle wall, but a single sheet of paper, it can level a throne. It carries ideas that outlive empires and laws that bind tyrants. It is the most subversive weapon ever forged. The historical need for paper. Can you imagine a world without the internet to share information and gossip, science and ideas, hearsay and hard facts? Some of us knew this world, but can you imagine a world without the television, without the radio? A world where a messenger or letter was the means of communication over distances. From time immemorial, wherever there was a leader, a king that ruled over territory and people, there was a need to keep records and communicate over distances. Thus appeared clay tablets in Mesopotamia, papyrus in Egypt, bamboo slips in China, parchment in Europe and the Middle East. But it was the appearance of paper that caused a social revolution lasting to this day. Knowledge, social upheaval, revolution, religious effervescence, legal and commercial practices, finance. This is a story of the chemical and sociological aspects of paper. Welcome to the podcast Chemistry Forging Civilizations. Chemistry, the science that studies changes in matter, changed humankind forever. The invention of paper. Kai Lun is a very capable manager and administrator. A few years ago, around the year 88 CE, Emperor He of the Chinese Han Dynasty appointed Kai Lun as political advisor and as his man in charge of all tools and arms production of the empire. Kai Lun's job and his close involvement in matters of the state, as well as the availability of a workforce under his command, helped him understand the need to keep records easily and efficiently. Kai Lun found the bamboo and wooden slips used for record keeping unfit for the large amount of record keeping required. Employing the workforce at his command, he designed a method to separate writable plant material from the binding components. What an irony it is! Kai Lun, the man in charge of all weapons production for the Han Emperor, ended up inadvertently inventing the most powerful weapon of all, paper. His challenge was how to separate the lignin component in the plant material from the cellulose fibers it holds together. Kai Lun used materials that are naturally low in lignin and high in cellulose-rich base fibers, which made them ideal for early paper making. Unlike wood pulp, they didn't require aggressive chemical treatment to separate fibers. Instead, he used an ash solution, which is lightly alkaline, soaking the material for days. He ordered to gather a slurry of mulberry bark, hemp rags, and old fishing nets, mashed into pulp, pressed flat and dried in the sun. This allowed microbes and enzymes to loosen the lignin and hemicellulose. Kai Lun's process did not chemically destroy lignin. It simply separated it from the cellulose fibers that he could use to write on them. His paper was not completely free of lignin, but it was by far a better option than the bamboo or wooden slips in use. It was much lighter and easier to write on. It could be used in larger quantities and carried without effort. Paper. What do you seek? Isn't it an irony that the man in charge of arms production for the Han Dynasty inadvertently invented the most lethal of all weapons? Paper. Leave your impression in the comments. Paper led to a wider spread of literature already in his lifetime. Kai Lun himself was appointed to supervise and oversee the 100 scholars working on the definitive version of the 5 classics of Confucianism. This philosophy is central to Chinese culture. Its influence spread throughout Asia. Confucianism even left its mark on the Japanese samurai Bushido code. This was the first social impact of paper, a modest start for what was to come in future centuries. The chemistry of paper. What if I tell you that paper is a distant cousin of sugar? Yes, the same sugar in your ice cream, in your candy, in your cereal, or in your preferred soft drink. Stay with me because I'll show you how they are connected. Drop a 1 in the comments if you know already. Nowadays paper is made from wood, which in itself is made of lignin, hemicellulose and cellulose. It is the cellulose what we want. All other components have to be chemically decomposed and eliminated. Lignin is an amorphous, complex and variable polymer, meaning its exact chemical formula is not fixed. It is formed of chains of variable lengths of 3 different components generically called monolignol units: p-coumaryl alcohol, coniferyl alcohol, and synapyl alcohol. In the broadest sense, the empirical formula for lignin is C9H8O4N, where N is a large number indicating polymer chains. Hemicellulose, instead, is a heteropolymer. It contains various sugar monomers. Unlike cellulose, which is a straight chain of glucose units, hemicellulose has short branched chains and includes different types of molecules that come under the general name of monosaccharides, building the unbreakable fortress with a molecular lock and key. Cellulose is a long unbranched polymer made up of many cyclic beta-D-glucose monomer units linked together. Each number refers to the location of a carbon atom. Each carbon atom has, of course, 4 positions to link to other atoms. D-glucose monomers, we said. Glucose can present itself in a few different forms. It shifts shape, but only one is able to build the unbreakable fortress that is paper. The letter D stands for dextrorotation, meaning this molecule, when illuminated with polarized light, will turn the angle of polarization rightwards. The wave theory of light describes it as electric and magnetic waves perpendicular to each other propagating in the direction of the observer. The wave of light emitted from normal sources vibrates in all directions perpendicular to the propagation direction. Light passing through a polarizer is considered polarized light, since only one of the directions has been allowed to pass through. Materials with optically active spatial configurations like glucose have the capacity to affect the angle of polarization of incident light. Glucose, of course, is one of the several basic sugar molecules in nature called monosaccharides. Because of their extreme importance in biological systems, whether vegetal or animal, they are subject of extensive study. Monosaccharides, glucose in particular, participate in the absorption of energy by living systems. They can exist in linear or cyclic form. In a water solution, 99% of the D-glucose exists as the 6 atoms ring called pyranose. There are 2 special isomers of cyclic D-glucose, also called D-glucopyranose for its structural similarity to the pyran molecule. Some cyclic forms are more adept to polymerization, meaning the bonding of similar molecules to form larger structures. In the beta form, the hydroxyl group attached to carbon number 1 is in the same plane as the methyl group comprising carbon number 6. The balls and stick model clarify this structure well. Carbon number 1 is referred to as the anomeric carbon, being the center of distinction between the 2 anomers, alpha and beta. In addition, both forms can adopt a chair and both spatial configuration, but only one can be the brick that builds a fortress, so that only beta-D-glucose has the lock and key potential to build the fortress. The both configuration is energetically less stable due to steric hindrance caused by the position of the hydroxyl group in the anomeric carbon with respect to the methyl group of carbon 6. But glucose is not only important in building paper. Chains of up to 10 monosaccharides, called oligosaccharides, are important in the energy absorption cycles of living organisms. The first step in the absorption of energy is glycolysis, the breaking up of glucose, to produce the pyruvate anion, which can be fed into the Krebs cycle, from glucose to cellulose. Beta-D-glucose has the exact key and lock geometry and spatial arrangement that allows the formation of the glycosidic bond between separate glucose molecules. Alpha-D-glucose instead has steric hindrances that force it to form short branched chains that lead not to paper but to starches. Starches can be attacked in digestion. These configurations are critical in the formation of polymeric forms like cellulose. They offer an optimal arrangement that allows the ordering of similar molecules into large polymeric structures. The glycosidic bond is an ether-type bond, a bond where an oxygen ends up in covalent bond with two alkyl groups instead of two hydrogens as in water. An alkyl group is, of course, a group with a carbon available for such bonding. The bond between any two monomeric beta-D-glucose is resistant to hydrolysis, decomposition in a water medium. The bond involves carbon number 1 of one unit with the carbon number 4 of another one, both sharing an oxygen. This is an ether-type bond that allows cellulose to build long fibers and makes it very resistant to decomposition. In our deep dive into carbon as the architect of life, we met glycogen, the branching baby brother of cellulose that fuels our muscles through 1 to 6 glycosidic bonds. But here, in the world of paper, the 1 to 6 branches are gone. Nature chooses a straight path, creating a linear fortress that can survive for 1,000 years. The chemical forces making cellulose a sturdy, resistant material. Cellulose chains are formed by the glycosylic bonds, but they are linked among themselves by means of hydrogen bonds and van der Waals forces. Hydrogen bond is a type of bond that cannot be described neither as a covalent bond, where two atoms share electrons, as the ether type of bond, nor as an ionic bond, where two distinctly charged atoms are kept together by electrostatic forces, like for instance in the common salt. An atom carrying a lone non-shared pair of electrons would act like a slightly negatively charged center, a nucleophilic center, attracting the hydrogen covalently bonded to another atom, thus creating a bond between them. The most common example is water. Van der Waals forces are a different type of cake altogether. They are weak forces, acting mostly at distances of less than 1 nanometer, a billionth of a meter. Their origin is the quantum mechanical fluctuations of electron clouds in each particular atom. Although they are very weak and transient forces, their sheer number makes them significant, particularly in keeping the cellulose chains together, forming a solid. Modern chemical treatment and production of paper. Nowadays, paper is produced first as a cellulose pulp using the Kraft process. Developed in 1879, the process treats wood with a mixture of sodium hydroxide, NaOH, and sodium sulfide, Na2S. The mixture breaks the ether bonds, of which lignin has plenty. Sulfur is liberated, many cyclic and linear fractions are obtained. Acids are neutralized by the sodium hydroxide. The brown mixture is produced with the many fractions resulting from the treatment, plus cellulose pulp. The pulp is separated, washed, and then used to produce the many types of papers. In parallel, the brown mixture is then recycled, concentrated by separation of the non-carbon chemicals, and burned. The energy liberated is reused in the process. Once manufactured, paper is submitted to different types of treatments, dependent on their intended use, from glossy magazine paper and food-safe packaging to durable banknotes and decorative papers. The effect of additives added to paper is physical in nature, how paper made modern civilization. Paper spread out from China to Central Asia and the Islamic world in the 7th to 8th centuries through the Silk Road, arrived in Europe by the 11th to 12th centuries. Paper was one of the greatest influencers of society for centuries in three main venues. 1. Communication and governance. Being easy to duplicate, easy to carry, and easy to store, paper became a tool of standardization of practices throughout vast distances. 2. Law, science, and administration. Record-keeping was now practical in a large scale. Tax registers, census data, legal codes, and land deeds could be copied, archived, and consulted. 3. Democratization of information and knowledge. The spread and popularization of literacy and knowledge through books, pamphlets, newspapers. Paper made the printing press and the surge of industrial printing possible. Literacy grew. After the appearance of the printing press, which mechanized the use of paper, people did not need to refer to intermediaries for knowledge. It made the spread of opinion easier to the point that it started the Reformation and the schism of the Catholic Church. 60 years after the printing press, from Martin Luther's 1517 first publication till the 1648 Peace of Westphalia, a century of upheaval and religious war was the direct consequence of the availability of paper and the mechanization of its use. In finance, paper revolutionized what money meant at all. Since merchants in Sichuan started closing deals with promissory notes through the issue of paper currency by the Tang Dynasty around 1020 CE, paper had to be accepted as money forcefully or by an act of faith in the issuer. At the end of the 19th century, most governments backed the printed money with gold or silver reserves. The use of financial tools spread, and so the need of government to print money to cover official debt, until the USA abandoned the dollar convertibility in 1971. Since then, money is accepted mostly by fiat on the issuing government. In antiquity, when currency was in coin, government could mint coins with less amount of metal or made them smaller for the same nominal value. Paper money made inflation more common, making the temptation to print money difficult to resist as a government tool for debt payment. Paper money is nowadays being displaced by special polymers that make it much more difficult to counterfeit notes. Paper is gradually displaced of its role in shaping society by the newest digital means to store and spread knowledge and by cryptocurrencies. Will paper still have a role in the future? Tell us what you think in the comments. Table sugar is a molecule we call sucrose, combining glucose in the form of alpha-D-glucopyranose and fructose in the form of beta-D-fructofuranose. What do you think of cellulose then? Having so much glucose in its molecule, could one make sugar out of it? Tell us what you think in the comments, and if you like our project, subscribe and you will receive a notification each time we publish new insights on the influence of chemistry on civilization.